Hi everyone. So this is the last session in chapter 6, which is using normal distribution as approximation to binomial distribution. So remember that, just I will remind you that the density function or probability density function of normal distribution, which is equal to 1 divided by sigma square root of 2 by e negative 1/2 x minus mu divided by sigma square, where x is any value from negative infinity to infinity. And we have the binomial distribution, which is combination x from n, probability of success to the power number of success, and then probability of failure to the power number of failure, where x equal to 0, 1, 2 till n. So note that here, this for normal distribution, the random variable is continuous, and for binomial distribution, the random variable is discrete. So which is this is very important. So for binomial distribution, we have, sorry, for normal distribution, we have two parameters: mu, the mean, and sigma, which is the standard deviation. Here, the mu equal to nb, and sigma will equal to square root of nb cubed. But the parameter for binomial distribution is 2. N, which is the sample size, the number of trials, and then b, which is a probability of success. So if we want to use normal distribution as approximation to binomial, then when we calculate a mu, when we use sigma, we will use this mu, which is the binomial distribution mean. And for standard deviation also, we will use the binomial standard deviation, which is here. So we'll use this one as mu for mean, and sigma equal to square root of nb cubed. So now, if we want to use this, we have to have nb must be greater than or equal to 5. Also, nq must be greater than or equal to 5. Okay, those one of the requirement. So now, as I mentioned, binomial distribution random variable is discrete, which is taking this value x equal to 0, 1, 2 till a specific number of tries, right? But for normal distribution, the random variable will be continuous, which is in this case x. It could be any variable from any value from negative infinity to infinity, okay? Which is really important here. So if we want to use normal distribution, then the random variable must be continuous. So how can we treat this? So we have to make this distribution, make this random variable discrete. How? Do you remember when we have a class, and then we did found the real limit or boundaries? It will be the same idea. So if we have those random variable 1, 2, 3, and so on. So let's say if we want to find the real limit for 2, then we substitute 0.5 from the lower limit, which is 2, it will be 1.5, and then add 0.5 to the upper limit, which is also 2, it will be 2.5. So for 3, it will be 2.5 till 3.5. For 1, it will be negative 0.5, which is 0 minus 0.5, and here 0 plus 1 1 plus 0.5, which is equal to 1.5. So now this is the our discrete variable in continuous form, right? Or after transformation to our transformation to continuous. So also we did know the requirement for normal distribution, right? For binomial distribution. So the first one, we have to have a fixed number of trials. So let's say that number of trials equal to 10, which is, I mean, n equal to 10, number of trials, n equal to 10, as an example, okay? And then maybe our x is number of heads. So if we flip a coin 10 times, and then we will see our variable x, which is the number of heads we will get. So if we do so, x could take any number from 0 to 10, right? And then the second one, the trials that are independent. So if that means that our results in first trial will not be affected, it will not affect the second trial, and the second trial will not be affected from the first result. So if we flip the coin and they get a head, and then in second trial might be I get head or tail, 50-50 chance, okay? And then we have two outcomes. One of the outcomes, if we got head, that means success. If we got tail, that means a fail. So we have two outcomes, success and failure. Also, then the probability of success, which is equal to B, must be equal from trial to trial. In this case, will be 0.5, right? Head and tail. So if we have those require, if we have this random variable, which is now binomial, and we have n times b less than or equal to 5, n times q less than or equal to 5, then we can use normal distribution. Remember that n lowercase n is the number of trials, x is specific number of success. For example, x equal to 3, which is out of 10 trials, we got 3 heads, okay? Then B is the probability of success in one trial, and it must be equal from trial to trial. And Q is the probability of failure. So, sorry, B is the probability of success, and Q is probability of failure. X is a number of success. So then maybe you could know that n minus x will equal to what? Number of failure, right? Number of failures in 10 in trials. In our example, it will be number of failures. So if we got x equal to 3, then the number of failures will be n minus x, which is equal 10 minus 3, which is we got 7 failures. That we got 7 tails out of 10. Okay, so we know that in the previous sessions that any sampling distribution, or we did, for example, the sample proportion, tend to approximate normal distribution if we have a large enough sample size, right? We did say, okay, if n is greater than or equal 30, and using the central limit theorem, we can say that the sampling distribution tend to be approximately normal distribution, a distribution that really close to normal distribution. So here, if we look to our sample size here, n equal 580, and B is the probability of success equal 0.25, And if you look to the sampling distribution, is really close to normal distribution, right? This is really close to normal distribution. So let's check here the requirement. So we must have a specific number of sample size, and this sample sizes must be simple random sample, right? And then we have B is probability of success. And we have also, remember, we have N independent tries of binomial experiment, right? So then the second step, we have to check that N times B greater than or equal to 5, and also N times probability of failure greater than or equal to 5. So if we got those, we then the next step, we find mu and sigma that we will use for normal distribution, using mu and sigma for binomial distribution. Remember, this is a mu and sigma for binomial distribution. And then we have to make sure that we have continue random variable, because x of binomial, it will be discrete, and N and X for normal distribution, it will be continuous. How we do that? By adding 0.5 or substitute 0.5 depending on the question. We'll see the criteria we'll do in this one in few minutes. So the procedure, we will do: one, check the requirement, NP greater than or equal to 5, NQ greater than or equal to 0.5. The next step, we will find mu and sigma to be used for the normal distribution. The next one, identify the discrete whole number X that relevant to binomial probability problem being considered, and represent that value by the region bounded by X minus 0.5 or X plus 0.5. The next one, we graph the normal distribution and shape the area and shape that desired area bounded by those values. And then, so let's apply those points in our example. So this our example, N equal to 580, which is the same example we saw last few minutes, okay? And then we have B, which is equal to 0.25, and remember that Q will equal 1 minus B, then it will be, Q will be equal to 0.75. And the question here, find the probability X will be at least 152, yellow bees. Okay, so let's see here. So now, if we want to use, so the first step, let's find this probability using binomial distribution. So for binomial distribution, we need N equal to 580, and we need B equal to 0.25, and we need the value of X, which is X here greater than or equal to 152. Okay, so now probability of X greater than or equal 152 equal to, let's go to stat crunch. Go to stat crunch, and then go to stat, and then do two calculator, first one, and then go to binomial, second one, okay? And then we go here, N, we have N equal to 580. And we have probability of success equal 0.25. And this will be greater than or equal, right? And then we have the value of here, it will be 152 compute. So this, do you see the shaded area in red color? And you clearly see this distribution is perfectly normal, right? It's normal distribution. But now we did use the binomial distribution to find this. So the probability is 0.26495. So it will be 0.2650. So let's write it here. This probability will be 0.2650. This is using what? Using binomial distribution. So now let's use the same, but using binomial normal distribution. So the second step, using normal. Oops. So the first step, if we want to use normal distribution, one, we have to have NB equal to what? NB, which is 580. So it will be, we must have NB greater than 5 and NQs greater than 5. Then for this one, NB equal to 580 times 0.25 equal to 145. So this is for sure greater than 5. And NQ will be 580 times 0.75, which is 3 times of 145, right? So if we do 0.75 times 580, it will be 435, which is greater than 5. So the first requirement is good, right? And then so this is the first requirement is okay. And then we have to check to find mu and sigma. So the second step here, find mu, which is NB, and sigma equals square root of NBQ here. So mu equal NB, which is we already did here, right? So this is mu equal to 145. And then sigma will be square root of 580 times 0.25 times 0.75. So sigma will be equal to 10.4283. Okay? So we need those. And then the third step, we have to find a real limit or the boundary for the random variable. So we need the probability of x greater than or equal 152. That's mean we need to find, since now if you look, 152 included, right? Or not included. So we want to just make sure, so if we will sketch down here, if we say that, okay, we have 152. So this is the value, 152. And then we find the real limit. The real limit, it will be here, 152.5. And let me change the color here. It will be 151.5. So we have to make sure that 152 is included. So it's greater than. So if we take 152.5, the area will be this one, right? Now we have to have, since we have equal sign here, 152 must be included. Then if you look carefully, we have to use this. So we did double check that the value of 152 will be included, right? So then we have to take x minus 0.5 greater than or equal to 152 minus 0.5, right? So the probability that we are looking for, which is probability of x greater than or equal to 151.5, okay? Or we can write it x minus 0.5, that's okay. So this is what we are looking for basically, okay? So now we can find this probability using what? Using StatCrunch, where remember that you will use mu equal to 145 and sigma equal to this value, right? Which is 10.4283. So let's go now to StatCrunch and try to find this probability. So now we will get probability, we compare it, then we will compare it with this. So now we have probability of x greater than or equal 151.5 equal to, let's go to StatCrunch and then close this, go to stat, go to calculator, and then go to normal distribution, okay? And then here we have mu equal to 145, and we have standard deviation 10.4283, and this is greater than or equal to what? 151.5, 151.5, and then we compute. We got this probability 0.665, 0.2665. So this will be 0.2665. So now if you compare this with this, is almost equal, they equal to each other, right? So this probability compared to this. So this is using binomial distribution. This is using normal distribution as approximation to binomial. So it's almost equal to each other here. 0.2650 and here 0.2665. They are very close to each other. So here the steps. So the requirement, we did say the requirement we must have NB and NQ is greater than or equal to 5. So this value and this value, both of them greater than 5, right? So this is valid. And then the next one, we find mu and sigma needed for the normal distribution. We use mu and sigma from the binomial distribution. And we got, this is the value of mu and this is the value of sigma. And then we have the probability of at least 152 yellow bees. This is a discrete, right? Because it's from binomial distribution, then a discrete, So 152, if we want to find the real limit for this one, it will be 152 minus 0.5, and then 152 plus 0.5. So we have 151.5 and 152.5. So those values is the real limit for the random variable, which is here, in this case here, this is discrete, and now here is in the continuous form. So now here we have probability of X greater than or equal 152. We did say that since we have this equal sign, so we must have this 152 included, 152 included, so it will be greater than 151.5. Why? Just to make sure that we include 152. So it will be here. So if you see it here, we have one, so this is the real limit here, and this distribution up here. So we start from 152 to make, sorry, 151.5 to make that 152 is included in the shaded area. And then here in this one, they use the table. We did use StatCrunch, so you can use the table too. You know that how to use table. So if you want to use the table, you can find z equal x minus mu divided by sigma. You got the value of z. Remember to use this value 151.5. Okay. If you did this one, you will get the this probability, which is here. Using the table, you will get this probability 0.2676, but we did use the technology and we did find this value, which is more accurate. So now we did find that the probability of X equal 152 or more success equal to 0.26. So sorry, 0.26. So now if you remember that we did say that if we have a probability of success, I mean probability of X and more success will be less than or equal to 0.05, then we can say that this is significantly high. So now this is 0.26 is greater than 0.05, then this is not significantly high number of success. So remember that just the continuity correction here, we just to make sure that we are include the random variable, the discrete random variable by using the correction factor or the continuity correction. So we either we use negative 0.5, I mean X, substitute 0.5 from X or add 0.5 to X. This is the table. This one I want to, so here in this one, so let's use the discrete here and use the continuous here. Okay, so here probably at least the first one they said at least 152. So at least 152, that's mean probability of X greater than or equal 152, right? Why 152 included? We include 152. Since we include 152, we have to make sure that we start from 152. So X will be greater than 151.5. Remember that if we put equal sign or don't, in this case is the same, right? So we don't need to put the equal sign here, since we know probability of X equal to 151.5. If we have continuous, it will be 0, right? And then the next one here, more than 152. More than 152, that's mean probability X greater than 152. So 152 does not include 152. It's not included. So since it's not included, then we can start from x greater than 152.5. Okay, again, it's if we put equal sign here or we don't, is exactly the same. Okay, the next one, at most 152, probability of x at most, that's mean it could be 152. It will be 152 or fewer. Then here we include 152. Since we will include 152, this probability will be x less than 151 point we include it. So it will be, no, it will be 1. We included, then we have to make sure that 152 is included. Then it will be 152.5. Do we need this sign here? No, it's the same. I mean, it's the same. If we did it or not, it's the same. Okay, the next one, let's do it here. The next one, fewer than 152, then it will be like this. Okay, so here does not include. So since we don't include it, so it will be x less than what? 151.5. Okay, the last one, exactly 152. So it will be here exactly. That's mean x equal to 152. Remember, if we have continuous random variable, probability of exactly equal to 152 equal to 0. But since we want to use the real limit, so it will be probability of that x between 151.5 and 152.5. If we want to write those, okay, or if you don't write them exactly the same numbers. So those very important when you solve any problem. So you, for sure, you will have one of those cases. So if you have this using using binomial distribution, then when you find the when you will use normal as approximation to binomial, you use this probability. Remember, here you will use mu equal to nb and sigma will equal square root of nbq. So let's see this one. So here, using the same information from the previous question, find the probability that probability of x equal exactly 152. Okay, so this is the discrete probability problem, right? The discrete. So when we want to use the normal distribution, this value, it will be x between 151.5 to 152.5, right? Which is this one here, the last one we did. Okay. Again, remember that we can use binomial distribution. So we have n equal to 580, and we have b equal to 0.25. So if we did go to StatCrunch, close this and go to stat calculator, and then go to binomial, right? And then did write n equal to 580, and the probability equal 0.25, and we have 152, and we have this is equal to, right? So this probability will be what? Let me write it down here. 0.0301. Okay. So this is using binomial distribution, normal, remember. So this one, probability of x equal 152 will be 0.0301. Here, when we want to use the binomial distribution, we need what? We need mu, which is equal to 145, and we need sigma, which is equal to 10.4283. So let's go to StatCrunch. So now we'll find this probability, right? So it will be probability of x between 151.5 equal to. So let's go do this one now. So let's close this one. Go to stat, calculator, normal distribution, and then come here to up there, up to the left here. So choose between, and then go to those values. We have mu equal 145, and we have sigma equal 10.4283, and we have our x between 151.5 and 152.5, right? And then compute. So this probability will equal to 0.0305. So this value will equal to 0.0305. So now look to compare those two results. So now this is the accurate result. This is approximation to this, okay, which is really close, 0.03 or 1.0305, which is up to the first three digits exactly the same. And then the next question, they said, find if this significantly high number of success. Okay, remember we did say that if probability of x or more success less than or equal to 0.05, then we say yes, this is a high number or significantly high. It's a high number of success. So this clearly you can see this value, which is 0.03, is less than this 0.05. Then we say yes, this is high number of success. So let's see here the question. So now we did find mu and sigma, which is we already know them, and then the probability of exactly 152. So the region will be between 152 and 151.5 and 152.5, and then this is the shaded area here, right? And then this is the value of probability using the table, right? Using the table, or yes. And then here they said yes, since we have the X success among n trial is significantly high, if the probability of X or more success, the probability of X or more success will be less than or equal to 0.05, right? Will be like 0.05 or less, then yes, we have 152 or more yellow bees. On the first question, which is, so this is the part A, which is we got that the probability is now, yes, here. So this one will be high number of success, but the relevant probability, which is 0.26, found in the first example, in general, the relevant result is the probability of getting the result at least as extreme as the obtained. But yes, but for this one now, we found that this probability equal to 0.0305, right? Using technology, then yes, this is a high number of success. And then how to use technology, we already did this one using stat crunch. And also you can use StatDisk for that too if you wanna do so. Okay, so that's it for this session, and good luck.